periodic table, which is made of cellulose. Cellulose, as you're going to learn, party people, is made up of glucose molecules, bonded over and over and over again. This came from trees. Trees collected energy from the sun, take CO2 out of the air, and made glucose. Now sometimes that's the glucose we can eat. Sometimes they bond it in ways that they use to support the cell. Guess what? A plant cell has to do what? Build and support new cells as it grows. So this paper made of cellulose, okay, has carbon in it. There's a lot of carbon atoms bonded together. Now, when I give it some activation energy,
It's a matching paper.
Wait, I just realized they're going to hear everything.
You've already said fire.
now,
Yeah.
if I give it some activation energy,
I love watching.
am I still giving it activation energy? No. But it's still going.
Yes.
It's still going.
Why would
It's
you
still
do
going.
that? Do that?
We have moisture in our hands.
Oh.
Now, what would have happened if I kept going?
It would have burned the paper.
Until what ran out?
The paper.
Did I keep the match there the entire time?
No.
So therefore, you saw something happen that was spontaneous, perfect. Why was it spontaneous? This is what you learned last night.
A spark to start it.
Well, you need a spark to start all reactions.
Well, you only needed it. You didn't need a continuous amount of energy.
It doesn't need to be on. When you spark your barbecue to start the propane burning, do you keep the spark on?
No.
Do you need a battery for a battery for a battery for a battery?
No.
No. So a battery works because it's set up that the universe allows it to go forward to give off voltage to power things. This will keep going. I do not have to keep a what? A light there. So this is spontaneous. And a spontaneous process is one that is self-sustaining. Okay? That will go by itself. Now, what's really, really important is that when something is spontaneous, that goes on its own, so to speak, it's self-sustaining, it's like riding a pony. Now, I call it the energy pony. If I ride a pony can bring me up the hill without me expending any energy. If something works, and there's a pathway for it to work, we get free energy out of it. They take fossil fuels in LIPA. They burn them. They boil the water. The water turns a turbine to create electricity. Why? Do we keep a spark on the diesel fuel? No, because the burning of the diesel fuel, once you start it, will continue. There's a pathway. Now, listen to me. You were right. It was spontaneous that this burns this way. Now, if something has a direction, spontaneity means there's a direction. In chemistry and biology, it means it happens. It can occur by itself. More importantly, though, if there is a direction that makes this burn, which means the carbon in the cellulose plus the oxygen makes CO2 and water, as I'm going to put up shortly, okay, as this is allowable, if the universe really allows this to go this way, what doesn't it allow?
Go back the other way.
Exactly. Have you ever seen CO2, okay, combining with what? Water, because these are the products, to reform paper and oxygen? You've never seen it. It just doesn't happen. Oh my gosh, there's paper forming. Okay, it doesn't happen that way. So that must mean what? There's a direction. If I wanted to make paper, and I'm going to fight the universe's direction, what must I do?
Use trees.
Give you the other analogy. I'm on the energy pony. The pony's letting me ride. It's giving me free energy. All of a sudden, the pony has to go up the hill, but it won't move. Now I've got to carry the pony. What must I put into the process? Right. So a non-spontaneous process is one which we have to add energy to keep it going. Once we stop, it stops. Think about photosynthesis. What is required in order to make sugar or glucose? You need sun, right. It's an autotroph, as we're going to learn in details. Does it work when there's no sun out? No. So it only works when there's light. That is a non-spontaneous process. It's being forced to work by the energy of the light. Ah, okay. So spontaneity is a measure of not just happening, oh my gosh, you're so spontaneous, now we're going. No, it means that we have a pathway. Now it's measurable by two things. So let's go back looking at your homework, you did a nice job. You had some great questions. Let's go to our Today website here. And let's go on to, as I said last night, let's go on to one of our first demonstrations. Okay? Let's do the whoosh bottle. Now, the whoosh bottle. I have an alcohol. Okay? It also has carbon in it with the oxygen. Now, the first thing is first, here's my alcohol. Okay? Let's do this one. Now, this alcohol loves to evaporate. Okay? At this temperature, it loves to evaporate. So it evaporating is spontaneous or non-spontaneous? Am I forcing it to evaporate? So it spontaneously evaporates based on a set of conditions. Good. Now, if it spontaneously evaporates, couldn't I ride that energy pony and get free energy? If somehow, okay, think about free energy this way. Water flows where? Uphill or downhill? There's a current going downhill, right? Have you ever seen, before there was electricity, mills and sawmills and factories develop around a waterfall? They were using the free energy of the flow of water from high energy potential to low potential to move a wheel that would move something, that would move a saw, or slam down on grain powder. Those are called mills. And they all developed on rivers, okay? And they gave the people who use the energy of the river free energy to do something because water flows spontaneously. Now, if you want to push the water up the river, what would you need? Tremendous amount of energy. So now you've got a good feel of what a spontaneous process is. So back to this. So in this demo, okay, it spontaneously evaporated. And now I'm going to react it with the oxygen in the air. Okay? Now, so, but as you've seen, you say I have to add energy for a reaction to occur, correct? I have to add energy for all reactions, as we're going to see today. But just so this one, okay, let's go see what happens. So this one's going to give off energy. It takes a little bit. Look at the little bit of energy I have and compare it to the energy that it gives off. Also look at something else. What are the components, the two components that define spontaneity? Well, number one, we know it's a pathway. You guys talked about order. The book talks about order and disorder, but the real definition, as we get to AP chemistry, is dispersion of energy. Now watch with me. There's two components. Look at this formula. I have 2 alcohol molecules plus 3 O2 molecules. Now, it's going to make, if they all react, a total of 6 molecules. You may say, Mr. Grodsky, I'm going from 5 to 6. But this is a big molecule, okay? These are smaller. Now, you say, okay, it seems to me that I'm creating more degrees of, there's what? 6 molecules here, correct? And there's what? 5 here. Now, think with me. Molecules. What really is the second law of thermodynamics? There's a direction. The best direction is heat flows from what? Hot to concentrated energy disperses out. That's really the second law of thermodynamics. You with me? So, molecules vibrate, correct? Molecules that are bigger, the molecules that are stuck kind of vibrate together. If you stuck 3 or 4 of you guys together and I asked you to dance, you couldn't dance as crazy, as independently as you want, correct? If I tied you 4 together, hold hands, and you had to dance, right? I'm not asking you to do that. Could you move with the same energy if you were by yourself individually? Right. Stuck together, we call that 1 degree of freedom. When you're individuals, you can actually do what? Give off more energy as individuals because you're not tied to the other person, correct? So as I go from 5 to 6, I'm increasing the number of independent particles. Am I increasing the disorder? Yes? Good. Am I increasing the dispersion of energy? Can't little particles disperse the energy more? Perfect. That's the first point. That we look at the particles. Look at something else, party people. There are 3 gas molecules. There are what? 2 liquids. 2 liquids and 3 gases make what? 6 gases. Don't gases fly around the room hundreds of miles an hour? Don't they have more energy than liquids? So I go from what? 3 gases to what? 6 gases. In fact, when you think about burning, you know what I think about? When this happened over here, when I burned the periodic table, carbon that was stuck together as a solid was free to fly around. Look at carbon has 2 O's and flies around. Carbon stuck wiggling in position. Once I burn it, reacted with oxygen, That carbon who was stuck in the cellulose is now flying around the room with 2 O's, hundreds of miles an hour. Who do you think is dispersing more energy? In the forward direction for the same reasoning. So for just the molecules alone, we have an increase in energy. So back to reality, let's light this. Okay, it might be a little loud. 1, 2, 3. Or not. Okay, there was a hole in that one. Yeah, that happens. Or you know what happened? I waited too long and it all evaporated out. So one more time. Now, there's a second factor. Okay, not only do we look at the degrees of freedom, we look to see if total energy is released. Now, if total energy is released, what does it mean? Look at that. That energy is on the product side. If I produce energy, where is that energy coming from? Out of thin air? No, think with me. Think with me. If energy is released, okay, you're an unsuspecting gas molecule flying around. You could be a CO2, and you're going around, flying around hundreds of miles an hour. And all of a sudden, boom, energy is released. And now you made me warmer. Am I going faster? And if I'm going faster, aren't I moving away faster? So I'm dispersing energy. So if heat's released, I'm also taking the gas molecules that now have higher temperature because you released it to them, and you're making them go faster and expand away. So increase of entropy, second law of thermodynamics, the direction to be spontaneous depends upon, are we increasing the degrees of freedom, going from a bigger molecule to smaller independent ones, and are we increasing the energy around the area to make the molecules that are already gases go faster and expand out? Is it logical that those are the two driving forces? And that explains spontaneity. So let's do this. Now, if I wait too long, it pushes out all the oxygen. Okay, so here we go. Try it again. All right. You know, I've got a hole. All right. I'm going to do it one more time.
This is working so well. Why did you pick the two like dented ones first?
Well,
Yeah.
conservation.
Oh, because they're gonna condense when you explode because of the gas that are being
I
released.
do.
You got this.
Oh, that makes sense because of the gas that are being released from the explosion and dispersing
Right, but the
out.
point is, it's not just so much the gas release, it's the heat. All right, one more time.
Let's do this. What's supposed to happen?
We're going to find out.
Are you sure?
Yeah.
If we have it.
Notice something, the liquid I poured, where did it go?
Down. It's on the side.
It's just on the side?
Yeah.
I poured liquid.
So it's not dripping out.
It went from a liquid to a
Yeah.
gas.
I just saw some drops.
There's some drop, sure. Okay.
Okay, let's do it.
Now if I wait too long, it evaporates out the oxygen. Okay. I know. So that the reason is it has to react with oxygen. Okay, let's see. Usually a surefire reaction. You ready? Okay, I'm done. I'm done today.
Oh, there!
Oh,
That's so
Yeah, it did
depressing.
well. Okay, so when in doubt, we go to
Can we
the.
watch a movie?
Yeah, what's
Is that what's so funny? That's so depressing. Dang it.
With a twist.
Oh.
Same idea.
Oh, we have to say it.
Oh, it actually worked.
That's so perfect. I love that though.
Hey, what is that?
That's a sparker. Okay, that's
And
what
we use
this
a
is.
sparker.
Okay? So this little spark is going to start the reaction. Okay?
What?
This little spark starts the reaction.
Yeah, why did we use that?
You shocked yourself.
We can love
So here we go.
Ooh. Oh, why did that happen? Can we try that again?
One more time.
Oh, whoa! I say we try it one more time.
I will.
But with the sparker.
I can't
Why
use
did
the
we
same
use
one.
Because once it's warm, it evaporates. Now, listen.
I thought you were just kidding.
Was that a spontaneous process? Was that a spontaneous process? Okay, why was it a spontaneous process?
Because it's self-sustaining.
You all talk at once. It's really cool.
It's self-sustaining.
It's self-sustaining. The little spark was definitely more energy. I can't wait too long. Okay?
Let's use the sparker.
Do it right now.
Okay, now. Let's take a look at your worksheet for a second as we wait. Okay?
You can't wait.
Take out your worksheet that I gave you. And let's go here.
Are we doing the gummies? We're
We're
gonna
gonna
waste
get there.
time.
We're gonna get there.
Wow, which one do you want?
Okay, take this one, please.
That's neither of them.
That's neither of them is correct.
I'm gonna watch this so
Here we go.
Yes, you do it.
You got this one.
We are
Okay.
doing that. Oh, we are? Yeah, we are doing that.
Okay.
But we're waiting
So-
too long.
No, we're not. We didn't wait long enough. All right, here we go. So,
So now we're not waiting.
in this reaction here, I'm going to melt some potassium chlorate. Now, when I melt that, okay, I'm going to have to use some heat or some MAP gas that likes to combust. So right here, I have some potassium chlorate. Now, I'm going to melt it, my time, into KCO3 to KCO liquid. I'm going from solid to liquid, yeah? Now, is that a chemical or physical change, you think?
Solid to liquid.
Yeah. Yeah, why is that a physical change?
Because they're not changing.
Correct. The chemical formula stays constant. Now, I want you to look at that as I do this demo. All right? Now, yeah. Now, we're going to find out in a second once I see where I am. Here we go.
Are you going to use this for the other class?
I'm going to try, although it seems...
Hi.
Okay, so we see our test tube. Potassium chlorate, it's a solid. Now, I'm going to melt it.
That is so.
Now, the reaction is in front of you. Okay, so first I'm going to melt it because I need to give it energy. So we're going to melt it. Stay with me for a second.
Jumbo's tall.
Flamethrower?
Jumbo. See this, Jumbo?
Now, let me ask you a question. I have two things going on here. I'm applying heat. I am melting this compound. It's getting there. Now listen. Which process is spontaneous? There's two processes here. You're watching a spontaneous and a non-spontaneous process occurring. So Emily, which one is non-spontaneous? Why is the melting non-spontaneous?
Because you have to put the heat on it.
Right. Which part is spontaneous? Why is the fire from this MAP gas spontaneous? Am I still sparking it? Okay. Now, in your worksheet, okay, what's the first question? Now, the little smoke you're seeing, some of it's evaporating. And now we've got liquid. Some of it's boiling, actually. Now, the reaction is, once I have the liquid potassium chlorate, I'm going to drop some sugar. The sugar I'm going to drop is in the form of gummy bears. Okay. Everybody ready? Okay, so now I'm going to drop some sugar. Now this was, I forced this to melt at room temperature by adding energy, yes? And now it's probably solid now. We would call this an example of coupling. John, what was your question again? How does things live by building? Does life go against entropy? Does life go against entropy? Does life build ordered structures? They're putting things together, correct? So it's fighting the universe. No, I can't give you these because he's been in the lab too long. Okay? John, I'm asking you a question. Stay with me. How do you think living things create and go against the... Am I going against the universe right now? Is potassium chlorate a liquid at room temperature? No. What am I doing to make it a liquid? I'm adding what? I am pushing the pony up the hill? Or am I riding the pony down? Right. I'm making a non-spontaneous process what? Correct. But I'm using a what process to do it? Right. Why do we eat? What do we break down? What do we break down, party people, when we eat? Glucose. Here we go.
Yeah.
Is this chemical reaction spontaneous? Am I there making it happen? It is happening because it's regular, defined by the universe. Let's take a look at your reaction. Look at your reaction. What are the two components to make a spontaneous process? What's the overall process? What's the overall process? I'm increasing that, what word? The disorder. We have a word for it. Second law of thermodynamics. Yes, it does. So entropy is a measure of disorder, which the universe wants, correct? But the life of a cell does the opposite. Life creates order. It wants to build things, proteins, bones. You guys are just complex little machines. From what? The resources that we eat. Yes? How do we do that? How did I make this happen? What did I use to make a non-spontaneous happen? Right. It's called a coupling. In order for cells to go uphill and carry the pony, they must have energy. Guess what they get the energy from? Breaking down glucose. Stay with me for a second. What does glucose look like? What does glucose look like? Sugar. It's C6, H6, H12, sorry. No, just stay with me. Now, plus oxygen, that's why we breathe, party people. Okay? It makes CO2 and water. I'm going to balance this. No. 6, 6, and 6. This is a solid that we eat, guys. What do we know? What do we know? One big molecule with a lot of carbon stuck together has what kind? Has what kind of degrees of freedom? Not many, right? Now, 6 molecules of oxygen have a lot, yes? But look what we make. 12 gas molecules that are smaller. There were 6 carbons, party people, right? Look, listen, there's oxygen here, carbon, carbon, right? And then we have some H's, but this now is flying around as a CO2. Each carbon is an individual particle flying around. What have we done to the degrees of freedom by breaking glucose down? Which is digestion. We've increased the degrees of freedom. Yeah, and what else have we done? Well, does anyone know that when you take carbon and react it with oxygen, what do you get? Sugar was in the gummy bears, party people.
Oh.
Do you think that gave off heat?
Yeah.
Do you think the cellulose and the paper gave off heat? Did you see my lame demonstration didn't work live? Did that give off heat? Okay. They all give off heat. So this not only increases the degrees of freedom, it gives off heat. What does the heat do? Makes the surrounding molecules go what? Why are we ectoderms? Why are we warm-blooded? Because when we break down glucose, we use its stored energy. Who created the stored energy? The non-spontaneous process of plants. So this, answer your best question of the day, John. Why living things fight the universe is that they use a spontaneous process. And they use the free energy of the spontaneous process to move that pony up the hill. To build proteins, to build DNA, to build and have more what? Cells grow, to be as organized, as complicated as we are as living things. We go against the universe because we use another source of energy to drive it like I just did. It's called coupling. That's how it happens. And if we don't have it, we don't have a source of energy, we can't fight the universe. And living things eventually lose to it. Okay? That's what this is about. And where's my connection? Because the first day better connect to the last day. We left off in genetics. And we talked about the E. coli had a way of what? Turning on a gene, turning off a gene based upon what it ate. If it did not have lactose, why would it spend energy to make the enzymes to break it down? So it keeps that operon what? Off, so it can use the energy that it took in as glucose for other living things that it needs to build at that time period. efficiency of energy must be something that organisms adapted to do, because if they didn't, they would have passed away and they would have died. So we are now talking about energy and how living things utilize it. But guess what? Whether it's living or not, we all live in the same universe. So somehow living things are using the laws of the universe to their advantage. And here they found something as a concentrated source of energy, which was made by the plants, and now we let it be free and disperse it, and we use that free energy. But there's one cost, and we're almost done here. The one cost is energy always must be what? Released. We must always increase the entropy of our universe. So no matter what we do, energy is always released. And therefore, over time, that's why they say over time, there's a loss of energy throughout the universe. We run out. We're going from a concentrated source to an unconcentrated source. But every process requires, whether it's coupled or not, energy to be released a little bit. That's why there's no such thing as a perfect motor. Here's something non-living. You can't have the perfect motor that's 100% efficient. In order for it to be what? To work, to have a pathway, to be spontaneous, a little bit of heat must be what? Released. Enough to make the process spontaneous. Take a break, guys.
This is like the first time I actually literally after.
You're killing it.